it will be the short presentation of the Moonshot sunrise done by Nathalie and Dario.
Thank you very much, Valérie. Before I begin, I'd like to express really a sincere thanks to all of the LUMA governance for putting together this beautiful days, giving us photosciences, what a great stage to be able to showcase all of our results and experiments. So thank you very much. So we have a Moonshot project that's co-coordinated between myself and Nathalie. We have a team composed of 7 partners. These are located in Bordeaux, in Paris, of course. We have 2 teams, as well as in Saint-Étienne, Lyon, Mulhouse, from which we just heard of from Olivier's group, as well as more recently in Marseille. The project has to do with improving photochemistry. Now, in photochemistry, we have since a long time, like in practically every area of science, right? We have certain dogmas, these truths that we use to kind of guide our trains of thought of how we see photochemistry and experiments. And some of them are actually very old, like, for example, the law of photochemical equivalence by Albert Einstein and Stark, which simply tells us that one photon gives us one photochemical event, which kind of stands to reason, right? We also know since over 100 years that resolution using light is limited by the diffraction to about 1/2 of the wavelengths. This is the Abbe diffraction limit. And even before that, Grotius told us that how much photochemistry we have actually depends on how much light is absorbed. Now, all of these principles are really rooted in our thought, and they help us guide how we see experiments. But when you think about it, they also limit how we see photochemistry and experiments. And when you, of course, understand that these laws of physics cannot be changed, they have to be respected here on Earth, anywhere in the universe, today or in the future. But nonetheless, thanks to advances in technologies, now we see them differently, and we can actually go beyond that. So we don't break these laws, but we somehow twist them a little bit, and we manage to go around them and circumvent them. So now we can use singlet fission to be able to generate 2 events from one single photon. Okay, less energy, but still 2 events. We can use, of course, super resolution imaging, and we'll hear about some of that from Marina's talk later this afternoon, to be able to see things incredibly detailed, like we've never been able to see them before. And as we just heard from Olivier, we can't change the way molecules absorb light, but we can change the way they interact with light, and we do that with osmotic interactions. And so the idea of our project is really to combine all of this and use this to improve how we can do photochemistry and how we see photochemistry. So the goals of the sunrise, of course, improve photochemical selectivity, activate inert compounds, like we heard maybe about the PFAS, exploit plasmonic interaction to control excited states, and then go beyond the resolution that's limited by light for this on large scales and apply it to things. So the project is, of course, divided in work packages. I'm not going to go into much detail because Nathalie will tell us a little bit more about our recent projects, so progress in this field. We have basically 4 main scientific work packages. The first one is oriented on the synthesis of the nanoparticles. This is done by Stéphane Parola's group in Lyon, in collaboration also with Olivier. We also have approaches to going beyond diffractive nanolithography using additive or subtractive photochemistry that's done at the PPSM. At the same time, we can do, or we will be able to do, single molecule polymerization like we just heard about, and then also go to plasma-coupled triple up conversion, thanks to some work by Antibouides in Bordeaux. We have, of course, the idea to put all of this together and try and do something that is practical. So we enlisted the help of Florent Maloggi at the CEA in NAM, and together with Nathalie's group in Saint-Étienne, they're actually going to apply the fabrication of these nano-resolved structured materials on large scale to be able to do photochemical transformations. So we could, of course, continue going on and telling you about the project, but we thought you might be interested to hear a little bit about the science. And so Nathalie now is going to tell us a little bit about the recent progress that we've had over the last year
Thank you, Dario. So actually, maybe you noticed some arrows on the graphs, and some of the work package have started last year, not all of them, so like this one, so I will not speak about the WP4, but now we would like to highlight some of the results, the main results that have been obtained within the Sunrise project during the year, and especially, so first in work package 1, so the work of Stefan Paola is actually well, so the team of Stefan Paola is actually well skilled for producing many kinds of metallic nanoparticles with anisotropic shapes, chiral properties, and also functionalizing them and including them in glasses also. So here we would like to highlight a result that has been produced with these bipyramids, so bipyramids gold nanoparticles, coated with gold that have chiral properties, and they actually collaborated with a team, with 2 teams in Brazil to produce a random lasing experiment. So in that experiment, we use a coupling between these chiral plasmonic nanoparticles with dyes, especially rhodamine 6G. And so this is mixed within a solution containing scattering nanoparticles, here, so titanium dioxide nanoparticles. And what they observed is the emission of circular polarized light with a very high degree of circular polarization, especially compared to the fact that the chiral molecules do not have a high dissymmetry factor. So this works led to an article that is now submitted. And the same team, and still in WP1, also studied the influence of the position of the emitter surrounding these chiral nanoparticles on the emission of circular polarized light. And for that, they surrounded the nanoparticles with very well-controlled layers, about 1 nanometer thick, produced by different layers of polyelectrolytes. And by controlling that, they could observe that there is an optimal distance at which the emission of circular light is obtained. So, and what is interesting there also is, so this work was carried out during an internship project of M2 students, and this M2 student actually got a PhD position in the Tornado Moonshot project. So this is to show that there are also cross-fertilization between the different moonshots. So here I will go fast because actually you have already seen that. So this was the first article within the Sunrise project where the team of Olivier Sopera working with the team of Stefan Paola demonstrated the fact that actually local plasmon-induced polymerization could occur, and especially they highlighted the fact that it was dissymmetrical in that case due to the fact that one edge of the bipyramid is placed on the surface and the other one is just in the air, so producing different kinds of polymerization on both sides. Now, so it's not WP3, but it's WP2, sorry, so for the 2 next slides. The team of Vitor Brazilians actually worked and focused on identifying photocage catalyst for localized ring opening polymerization of biosource monomers into polyesters. And when doing that, actually they also monitored in situ the reaction of polymerization, and they identified that there was different action speeds of this polymerization, and also they could highlight some unexpected mechanisms like bubble formation. They used also different inline characterization techniques like UV visible spectroscopy and liquid chromatography, mass spectroscopy to identify the uncaging of the catalyst, or also identify different intermediate spaces in the reaction. And what is interesting also, they collaborate with the group of Institut Fresnel now, so to study in situ using quantitative phase imaging the polymerization process. So they can detect very low amount of polymers directly forming on the substrate. And in that case, by following in time the process, they could optimize the process and select the right concentration of monomers in the solution. And so specifically on this phase quantitative imaging technique, so led now by Pascal Berthaud, who has moved at Institut Fresnel this year. Actually, they try to improve the sensitivity. And to do that, they especially use spatial filtering on the setup that actually allows to balance the continuous background with a scattered field. And this allows to improve significantly by typically 1 order of magnitude the sensitivity on the phase measurements. So this allowed for optimizing experiments, for collective experiments, and also to probe in operando the polymerization around the plasmonic nanoparticles, detecting really the formation of a nanometer thick layer of polymers, so very sensitive technique. So, and to conclude, because I'm already late, sorry, just to say that actually we hired only 1 PhD student in Sunrise from the beginning of the year with the funding of Sunrise, but we work also with 2 other PhD students who were hired through supplementary fundings, also working with M2 students, and now we are growing more and more, so from 1 month, with a new PhD and postdoc student joining the project. So thank you very much for your attention.